Hello guys, I'm going to talk about the example about robust Poisson regression for the binary data. So I'm going to talk about this example in 5 parts. First of all, I'm going to give you a brief introduction about the data, and then I will tell you how to compare and pick different features to predict the binary results. And also, I'm going to run the Poisson regression and the binomial regression to compare the test. And also, the most important part, I will use a robust method to improve our Poisson regression, and then we can compare the new method with the old Poisson method, and then we'll probably get a conclusion to compare which method is better. Alright guys, so let's first take a look at the data. The head function will give us a brief looking of our data. So we can see that test is very obvious binary data. It tells if a patient has diabetes, then the test will be positive. If a patient will not have diabetes, will be negative, except the pregnancies and ages. All the columns here are continuous variables, so we may use them as features to predict our binary results, which is a test. The first step is to replace the binary letters into the digit numbers. So basically, in this function, I'm saying if the test is positive, then it will be replaced into 1, otherwise it will be 0. And also, I think there are like a couple of missing values in different columns. So those two lines will give us a brief looking for how many missing values they will be, and also what percentages of values are missing. So from here we can see that almost half of the insulin data is missing, and also almost 1/3 of the triceps data is missing. So typically we use each column's mean to replace the missing value. So for example, here the glucose, basically I'm saying if the glucose data is missing, I will replace it with the mean of this column. So these 3 lines will fill in those missing data. Next, let's take a look at those features. Alright, let's check what features we need to pick to predict if a patient has diabetes or no. In fit 1, I choose the glucose because glucose is rather important to decide if a person has diabetes or not. And the second one, I include the diastolic. So let's first check those two. Also, by the way, the GLM here means general linear model, and the method we choose is from the Poisson family, and the ANOVA fit 2 tell us the relationship between the second feature and the first feature, which is a diastolic and the glucose. So here we can see that the p-value for the second feature is rather large. So that tells us we need to reject this feature. So in phase 3, I try to switch the order with BMI and diastolic. So let's see here. So for the BMI feature, we got a very small p-value, which means BMI somehow can be a good predictor. But again, diastolic here has also a large p-value, so I will not use diastolic to predict the diabetes. That also makes sense because diastolic, that's more like blood pressure, so maybe there is no relationship between him with disease. So the ANOVA function here tells me that the diastolic features is not suitable to predict if a patient has diabetes because its p-value is rather large. So that means we will drop this feature. So finally, I decided to use the glucose and the BMI, those two features, to predict if a patient has diabetes or not. So the first fit will be the Poisson regression method, And the second fit will be the binomial logistic regression. We can see here in family, I choose binomial, and inside link, I choose logistic. So let's take a look at the results. So here it tells me that if I'm using the Poisson regression method for the first patient, I will get 46% chance that he or she may have diabetes. On number 2, like the patient might have 11% chance to get diabetes. So let's trace back to our original data. So if a person's test is positive, like in number 5, that means the person might have very high chance to get diabetes. So here it has like 55% chance that the person has diabetes. In number 6, which is negative, the person only have like 20% chance to get diabetes. So that makes sense. And let's check for the binomial method. Okay, so for the binomial method, somehow they are matching because first one is more than half chance and it's positive. On the second one, the person only has 6% chance to get diabetes, it's negative. On the number 4, like 8%, it's negative. So that makes sense. And the summary function will give us like more details about those two different methods. The first one is the Poisson regression. So it gives us the coefficient, the intersection beta 1 and beta 2, and also give us the standard error of beta 1 and beta 2 and their p-values. Same thing here for the binomial logistic regression. We can see that their intersection are rather different, as well as the beta values. So let's check for detail for their confidence intervals. For the Poisson regression, it has a narrow interval, but for the binomial method, it has somehow larger confidence interval than the Poisson regression method. So in that case, we probably can say that the Poisson regression method is somehow more accurate than the binomial method. Okay, so now let's take a look at the robustic regression method. In previous video, I think you already know that the robustic regression method is to help us to lower the variance and also make the residuals smaller and also to improve the accuracy of our test. And also, I think you remember that there is a matrix calculation. The matrix looks like a sandwich. It's a huge calculation over there, but here we only use the sandwich library. Will give us a very easy result. And the second library is just to give us the robustic standard error as well as the related coefficients. So I'm still using the Poisson regression, the previous fitted function. The only thing different is that I replaced the covariance here with a sandwich value. So let's take a look at the new fitted value. So compared with old one, pretty much they have like the same intersection and the same beta 1 and beta 2. They are slightly different, but the major difference is the standard error. We can see that for the robustic method, the standard error is significantly dropped. And that will make our confidence interval smaller and also somehow more accurate. Remember before we used the log transformation. So here I wrote a function which just to give us the expectation of everything we want. So first of all, let's take a look at the robustic method as well as the Poisson method. It gives us two coefficients. This is real coefficients we want. The beta one, the glucose, here means that if a person's glucose is increased by 1 unit, the chance of that person might get diabetes will be increased by 1.8%. And also for the BMI, if a person's BMI is increased by 1 unit, the chance of that person might get diabetes probably will be increased by 0.4%. Now let's compare the confidence intervals. So for the Poisson method, the confidence interval will be, for the intersection, will be from 0.4% to 1%. That somehow makes sense because basically, if a person is dead, which means the other features are zero, the person will have zero chance to get the disease. And let's take a look at the confidence interval for the robustic Poisson. The first one is for the intersection part. It's from 0.5% to 1%. And for the glucose, it's from 1.1 to 1.2. We can see that the confidence interval of the robustic Poisson regression is slightly smaller than the regular Poisson regression method. So somehow we can say that because the robust standard error has decreased, so that the accuracy has been increased. Alright, so that's it for the robustic Poisson example. Thank you guys.